talk is about an application of the fractional order modeling to study drug diffusion, and our speaker is Tahmineh Azizi from the Washington University in St. Louis.
Thank you so much, Liam, for the introduction, and thank you, Fawn, for being here. And as also Liam mentioned, I'm going to be talking about how we can apply a fractional order modeling approach to be able to model drug diffusion in pharmacokinetic modeling area. So this is like a topic of research that when I was a graduate student, I was interested in knowing about that after doing a lot of integer order modeling, and let's move to fractional order modeling. And so I just focus maybe just a very simple and basic just definitions, application about fractional order modeling for the purpose of just the conference. And thank you so much for the organizer of this amazing conference for having me again this year. I'm so excited to be here. So let's start by just simply defining a mathematical statistical model like objectives, which I'm doing mathematical modeling, so I've been done a lot of different modeling, but in general, just mathematical statistical modeling that are going to help us to, for me as a biomathematician, to understand the interaction between the different compartments or components of a system biology we have. At the end, we are going to use this mathematical model that we develop to predict the future of different biological models, because we don't want to sacrifice more animals. That's just a simple, I would say, reason for having mathematical model. Having this model is going to help us to predict the future of biological system. Just for having like a model at the end to work, we need to really perform some experimental like we should have some experiments to be able to validate our model using like different experimental data that we have. Test our model and evaluate that. For example, if we are going to understand for the purpose of this presentation about the drug distribution in different body organs and how it interacts with different tissue around like in entire body, we need to have like a comprehensive modeling approach that is gonna capture all of those complicated like phenomena that is happening inside body. So we are gonna just, as you will see, that just simply use a system of ordinary differential equations that undergraduate students are actually doing a lot to model all of these important processes like drug distribution, absorption, and metabolism, excretion. And these are the good thing about them. They are flexible. We need them because they are flexible to any update, any modification that we are going to apply in the system. So the first modeling that approach I'm going to present, maybe just in general, in a bigger scale, is going to be a model that we use for entire body, which is called a PBPK model, which is a physical, like physiologist pharmacokinetic modeling approach. So this model that I put in the right-hand side of this slide is maybe not that much clear, but as you can see, there are different compartments in this model. Depends on, I would say, availability of data. We are going to include different body organs like brain, heart, lung, stomach, and maybe stomach is going to have interaction with the intestine, or having liver in there, also kidney, skin, fat, bone, muscle, and many just other organs, just in general. For example, for this specific study that I was working on that during PhD. And also we need to include a different way that we are injecting the drug intravenous, intramuscular, through, for example, you're going to apply drug through food or water. And we are going to consider all of these factors for when we are going to do a PBK modeling. So you give some input to this system, to this model, which are going to be some biological, physiological parameters. And as a mathematician, we are doing the modeling, considering all of this interaction between different organs, and also considering, as I said, different way that we are administer the drug, like intravenous, intramuscular, and other ways. And then we are going to provide this output, which are going to be the concentration of drug in different tissues or body organs. So, and then finally, we need to validate the data that we have. For example, here, it's actually a simple model that we developed for oxytetracycline for different drug formulation for that, for swine, for animal. We didn't extend it to the like human model. So this is a general like modeling approach that applied a lot when we are going to start, for example, testing a drug and we use animal experiment. What are the building block of this PBK model? So we need to have to put some information inside of this model in this system. So the important one is really, as a mathematician, we need to have some information about the physiological parameters. So it's like a collaborative actually work that we need to do. So for example, about the anatomy, about the physiology, about the organ volumes, which is important, surface area, about the tissue composition, blood flow rates, and expression and like level, and there are many more parameters. Depends on which organ specifically we are looking at. We need many other parameters, values related to just drug specific like parameters, we call them. As I said, there are different other factors that like chemical parameters that we need to include. Also, formulation of the drug is important for us. For example, we have a long-lasting drug or short-lasting drug. Study protocols are also important for us about, for example, different dose and dosing regimen that we are going to use for a specific project. About, for example, as I said, different formulation and that we are going to use, and maybe food intake and exercises, and all of these factors need to be included when we are looking at the PPK modeling. Or maybe someone is interested to model different scales from just a cell scale to organ scale, starting from the micro scale model and just go to the just bigger scale, like a micro scale, which can be organ, like heart here, you can see. And we are just using this, for example, multi-scale, they call it modeling approach for the purpose of disease modeling, drug monitoring, toxicity, study and using studying the different mechanisms of a drug and interaction with different organs. So these are like a different modeling approach. Maybe if someone is going to go into detail, can consider, and is has been done a lot. But let's make it as simple as it can be, but not simpler. This PPK model is really just a huge type of modeling. Actually, it has been done a lot. It's not something which is not impossible, which is not possible, but just as I said, we are gonna do something very simple. Let's start from simple integer order modeling for just some specific like part of the body. We are not gonna include all of the organs here and write the fractional order modeling. But before starting, let's talk about this approach that we call it as PK/PD modeling, which is actually the main or foundational, like I would say, foundation of our mathematical modeling here. So pharmacokinetic models, we need some important factor here, like external exposure for chemicals or drugs or nanoparticles, for example, about the absorbed dose, about the like internal dosing that we consider for this type model. Also for the pharmacodynamic model, we are interested in other other factors like in molecular interactions, for example, receptor activation or inactivation, or we are interested about the cellular responses, for example, increase or decreased cell size and vulnerability, or about the like therapeutic or toxic responses that we get, and other, for example, functionality of organs that happen, and also about at the end we are gonna do this approach to be able to model different like type of disease. And for all of this, like that I defined here, we need a tool to be able to relate this internal concentration of like active compound that we have, just can be compound that we have, can be any of this chemicals, drug, or like particles. And we need the information about this target sites that we are interested. For example, it can be a tumor, and also the chemical, also dosing and chemicals, chemicals that we are going to give to a human or subject. What tool can help us to be able to just relate all of these information, which is called just as simply pharmacokinetic or pharmacodynamic modeling. We are going to combine them. Actually, we need both of them at the same time to be able to get a PK/PD modeling approach, which is going to like a study simply just the effect of drug and how it is changing during a time. So for the pharmacokinetic modeling, we are interested to see what the body does to the drug, and how the drug is going to be absorbed, distributed, or metabolized, excreted, or eliminated from different tissues, or just from body. And for the pharmacodynamic is what exactly drug is going to, for example, do for to our body. And we are interested to know about the therapeutic effects of the drug. How it's going to work in our body. So we are going to combine these two approach at the end to have a PK/PD modeling approach. So just drug distribution through body, as I said, we are going to use just simple modeling approach, which is called compartmental modeling. We are going to divide our body into different compartments. And here just that I used here, this just refers to the rate of distribution of, for example, drug to different tissues that we have. So we are going to just model this process through different body, like from like distribution to just elimination of the drug. And we just use simply a system of differential equation to do that. And then we are going to extend it to be a fractional-order system. So just a start from the simplest, I would say, modeling framework that can be done just simply when we are just interested to see just how the drug is going to go from a capillary bed to the tissue. And this two just compartment model here, there are some rates between different tissues, and we are doing PK/PD modeling, so we are also approximating this rate, which is important for us. Also the K24, which is the elimination rate. We are approximating just simply using a mass balance equation that we define here, as we can see in the right-hand side of the slide, and all of this mass of drug, specific drug that we have in different tissue, like capillary and then tissue, which can be a tumor for us, for example. And so just we give it to the students and they solve it like numerically, and what we just get just this mass of drug in different tissues. But this is just a simply like integer order modeling, and maybe we are just simply solve it, for example, like here explicitly, and just give an analytical solution for that, and just study the of this drug in different tissue. But we are interested in more. We are gonna do more. Maybe this integer order modeling is not the right model for us. Of course, when I say that, means that at the end we need to really validate if this modeling approach that we are presenting here as a fractional order modeling can be a right model, which fractional order that we are going to use is going to be the best for us. So I'm going to introduce just this fractional differential equation at the top of this slide, and A is just using A, which is for example here, mass of drug in different tissue. Just I kept it as A here to be consistent. And then so we have different type of fractional order derivative, like but I'm gonna use here this approach. In this approach, we are gonna actually introduce this Grünwald-Letnikov approximation for our system. So there are, for example, this approximation that we use is for this type Riemann-Liouville fractional order system that has been written here in the third line of this slide. But there are other type of like fractional order derivative, like Caputo derivative, that can be also another candidate for like formulate a fractional order differential equation. And then we are just using, for example, a nonstandard finite difference method, like a mechanism, like scheme to be able to discretize the model as what we usually do. And then we are approximating the coefficient of this Grünwald-Letnikov approximation that we use for our specific Riemann-Liouville just fraction order model. So this is just all of the steps that we are familiar with that when we are doing, even when we are solving discretizing just integer order model. So we do the same thing, but just different tools applied here. And then the best thing here, maybe I just say just what we are interested in is this parameter, which is order of derivative, or I hope everyone can see my mouse is moving. This order of derivative is going to help us to control the behavior of the system. At the end, you're going to change it between, for example, just 0 to 1, and you're going to see which, for example, maybe if you change it continuously, you're going to see how this behavior is going to get close to the integer order model. But still, as I said, we need to have really data to be able, experimental data to be able to say which model is going to be, which order of derivative is going to give us the best candidate for this, for example, for this specific purpose. For example, this specific study, we just had this model here in the top right hand side in the integer order formulation, but now we used this Liouville formula, and then we approximated using the just Grünwald-Letnikov approximation, and we discretized this to be able to provide this analytical solution. And just we plot for different order of derivative, for example, just put some of these orders. And maybe, for example, we are interested to see which rate and at which rate, for example, the drug is going to be infused into the capillary. And we have this rate. We have just added another rate to this compartmental model that we have, just simply writing the mass balance equation. And again, do all of the steps that we approximate the this fractional order system using a Grünwald-Letnikov approximation, and then discretize it just to find this new system that we we have in this slide, to find a mass of drug in different compartments, which can be capillary bed, and then, for example, tissue, which is just more. So this model is actually are tested with experimental data. So here we just have this integer model, but in fractional. Here we have, sorry, this integer order model that we are gonna write down as a fractional order system. And so just analytically, we just solve it, and we have all of these rates approximated simply for this study. But as I said, we are going to see what if we are we're interested to see this if we can really get a better or more exact behavior of drug distribution just using fractional order approximation and fractional order modeling, as we approximated this fractional order solution for the system. And then just having different order of derivative, we get like different behavior for the solution of the system, which is what we had it before. But let's talk about like a more, let's add more compartment to the model, not more rays. And this new compartment is going to make it more, I would say, realistic model, which is endothelial cells that are covering all of the blood vessels that we have. So maybe it's going to give us a better model. As you can see, just as simply, maybe I just draw this very simple like model here. And for example, you have any specific drug or any particles, any chemicals, which is going from arterial and then capillary, and then the target tissue, which can be a tumor, and then going back to the venous. So we are modeling by adding a new compartment, which is endothelial cells here. So we are interested also to see how what just the concentration of this specific compound, which can be nanoparticle, any chemicals in endothelial cells as well, which are going to be actually between capillary and target tissue. So we are adding this compartment here, and we are going to just ignore. We are not going to include these surrounding cells of endothelial cells in the modeling approach, but it's better to have. And so we are going to divide it into like this tissue, which is shallow tissue or deep tissue. I'm going to call them, and having this new compartment. Let's see if we can get like better solution or not. So we have different rates coming from material, this infusion rate, and then all of this rate between different compartments, and again, a rate of elimination. So using this just simple integer order modeling, we can simply approximate all of these rates and find the concentration of drug that we have in different tissue. This can be a really, I mean, good, but simple project for undergraduate students. As I remember, I was telling to one of the students that I had. So just writing down mass balance equation, simply modeling this biological system, biological process, and just having a lot of actually assumption for this, for example, if this is a really project, and finding the mass of drug in different tissues. Students easily can find out the solution and just to find out what is going to happen for this drug in different tissue, how it's going to change the concentration of the drug. But again, this is integer order modeling. Let's have fractional order modeling actually added to this, maybe a study project for students. And this is going to be interesting because, again, we have like fractional order derivative, and they're going to like just use this non-standard difference just a scheme to discretize the model and find this analytical solution and play with the parameters, control parameter or order of derivative, and get different behavior of the system. So it can be just, I would say, a good project for undergraduate students that can apply and see really behavior of the drug, just how we can control it just simply by using different order of derivative and finding the mass of drug in different tissues. As I said, this type modeling has been applied in different areas, not only biology. We just decided to show it because it was a project that I was doing during PhD, and I was working with the undergraduate students. She was very interested, and so I selected for this topic. Also, I added this, for example, maybe more advanced modeling. I just call it like fractional order modeling, just to be able to say, yes, we can really just move on from integer order modeling to a just maybe more comprehensive modeling, having like this control parameter, this new parameter that we introduced to the system. We are going to be able to control the behavior of the system and provide more dynamics that, of course, at the end needs to be tested using, if you have experimental data, to see really which model is going to be the best candidate for the behavior of the system. This system can be biological system or physical system based on application. I have seen many applications for fractional order modeling. As I said, there are different type of modeling, like fractional order derivatives that people use, like Caputo is one of the really most common type of fractional order derivatives that has been like applied a lot in different areas. And definitely just having this having more control on the behavior of the system would be the one of the advantages of this type modeling that I'm advertising here. So thank you so much, everyone, for your attention. I hope this is useful for the students, if you have any student here. And I'm going to thank the organizer of this amazing conference for having me again. I'm so excited to be here, and I'm here also to take any question if anyone has. Thank you so much.